So I'm going to talk a little bit about Xilinx and big data, mostly on the tape-out prediction scheduling. I don't want to minimize the security aspect of it. To me, that's just a slam dunk. It's not something that's optional anymore. You just have to do it. So Xilinx, in case you don't know, is an FPGA company. Some stats on the company there. Should mention now that we are the only Tier 1 FPGA company that's still independent. So buy from us, not from those blue guys. And if you have any more rumors about who's buying us, please let me know. I have no more idea of what's going on than you do. I'm always open to rumors. So the real question is, when it comes to tape out, the questions that come up are, when are we really going to tape out? And who's having problems that we don't know about yet? There's always the project down, top-down schedule that people have. That's generally reactive, not predictive in nature, so it accommodates problems after they become visible, not before. And then the third thing that usually comes up from finance is, where's all this extra money going and who's spending it and why? Specifically, which series and which IP design blocks are using extra resource, whether it be licenses or people? And we need to be able to come up with an answer for that so that we can either plan or correct next time through. So the standard answer to when are we taping out is usually lots of meetings and lots of Excel. People have weekly meetings, they put stuff into spreadsheets, they make graphs, it all looks good. The problem is that engineers generally want to clean their laundry in private. A problem isn't really a problem to an engineer, it's an unsolved challenge until it's irrevocable and they have to go admit it. So you tend to find problems late because they don't consciously but unconsciously feel like it's something they can solve without having to make a big deal about it. There's a lot of wisdom from previous projects that people apply that sometimes applies and sometimes doesn't, and generally you don't find out what doesn't until the end. So retrospectively you know, but at the time you don't. And what you generally get is a reactive system that tells you why tape-out was delayed, but doesn't tell you it's going to be delayed beforehand. Now, this is a bit of an oversimplification. It's a much more complex problem than this, and you can obviously witness problems as you go through the project, but in general the current model is a reactive model, not a predictive model. So there are many answers to the problem, but one of the key features is taking the human element out of the raw data collection. People want to put their bias on it. The way to do that is to take the people out and just collect the raw data and analyze it impartially. It's hard because there's a lot of raw data to do. You don't know which data matters and which doesn't at the beginning. And extracting something useful out of a large amount of data can be quite a challenge. What you want is your smart people thinking about what useful data is, not spending an awful lot of time trying to extract it. So what's the answer? What do you do? Well, really what you want to do is build a system to collect and store lots of raw data because you don't know what's going to matter until the end. And you'll change your mind as you go through the project as to what actually is important or not. And you want to efficiently process a large amount of data into a couple of small key metrics that you can use to predict. You may not know what those metrics are at the beginning, but as you walk through, you'll start to understand what matters and what does not. And then you can use your smart people to think about what all those metrics mean and how to assemble them into a prediction. So the questions we want to answer are, when are we really going to tape out? Who's having problems? And from finance, where's all the money going? What that usually translates into is there are some long pole processes for tape out, and for each of those there's some data associated with it that's in your data management system. You can use that data as a proxy for where those processes are at. What you want is some metrics that cover that data type. And for instance, for open access data, you want check-in and check-out times and license usage. For DRC, you want the number of errors reported. Each data type has its own metrics that matter, but you can correlate a process with a data type and therefore with some metrics that you can use to track that data type. So you just collect them and do a prediction. How hard could that be? So a lot of that's very theoretical and high level. What I'm going to show you is more of a practical example because I think that makes more sense than some high-level slides. To that end, I'm going to assume that custom layout is my long pole. There are many of them, and the technique is different. This is just one example of one metric and one area that you can use to track into a prediction. So if you assume that custom layout is one of your long poles, what do you need to be able to predict the layout closure timeline on a project? You need to know how many man-hours people spend on a particular block or IP, and how long it took on the previous project and how long it's taken on the current project. There's always a process scaling factor. When you go from 28 to 20 to 16, stuff just gets harder. It takes longer, it takes more runtime, takes more manual effort from the design teams. So there's a scaling factor for the process node that is relatively consistent, but you need to know what it is. And then there's a complexity scaling factor. Designs tend to get more complex with each generation. Some stay the same, some add features. Very rarely do they get simpler or easier to do. So there's also a scaling factor for complexity that you've got to factor in. So the equation is really easy, E equals ms squared. How hard could that be? The problem is if you just do that blindly or dumbly or generically across the entire design, generally what you get is a very wrong answer. The problem is the error bar on it is bigger than the prediction bar, so the window of opportunity for early to late is very big. So if we have a perfect metric system, one that doesn't exist yet, what you really want to know is when was the cell checked out, when was the cell checked in, who did it. One person editing 5 cells for an hour counts the same as 1 cell for 1 hour. It's the same library, it's the same IP design block, it's the same person. You don't multiple count each cell. You want to know which IC manager library it was done in, because those correspond to various IPs, and there can be many libraries in a single IP. And you also want to know when the users checked out the license and then had the license taken back off them because they weren't using it. Checking out the license and going for a long lunch break doesn't count as man hours. So what you want to know is what's the actual man hours they used on the design, not how long did they have the tool checked out for or how long were they in the office. It matters getting down to accuracy here because what you're trying to do is minimize the error bar and the final predict, and the details really do matter. If you do this in a more coarse and generic matter, the answer you get won't be very accurate and your prediction won't be very good. So you have all that, assuming you have all that raw data, you have the total man hours per design team. You want to know for that design team, when do they typically start on a project, when do they complete, what are the transition dates from one project to the next, and from one data view to the next, when do they go from RTL to schematic, schematic to layout, for instance. So what you get is a big set of time series databases with different intervals, some are days, weeks, months over a project. Once you've got that, you can start predicting, based on the previous project and your scaling factors, what they should be doing in the next project. So what you do, at the start, you take a wild guess at what the process scaling factors is, and the error bar on that is fairly huge, so you don't tell anybody what your prediction is because it's not very substantiable. But as you go through the process, blocks and blocks come clean in your current project, and that will give you some quantifiable metrics as to how much extra is the layout effort compared to last time, how much is the complexity scaling factor for a particular design. So you can start taking the early blocks to go through and using those to refine what your early estimates are for some of these scaling factors. And that, obviously, as the project goes through, you get more and more data to base that on. You can use those early blocks as the starting point for your estimates for your late blocks. So you get to refine the later blocks that haven't yet started based on the same assumptions as the early blocks. And those scaling factors can be different for different styles of blocks. Mixed signal designs look different from high-speed digital, look different from standard P&R digital blocks. So you have to kind of group your designs into styles and then apply factors for each style. If you do the same thing across the board, again, you'll get kind of incorrect answers. What you want in your metric system is something that just makes that easy to do. You can do it all by hand in spreadsheets or Perl scripts or Python scripts, but it's kind of a pain in the ass. What you want is a metric system that just takes all that data and gives you an easy way to get a simple answer out of a very large amount of data, so you can focus on what does the answer mean as opposed to how did I get the answer in the first place. And it's got to be easy to generate this data often, because as you go through the project, you're going to rerun this on a weekly or even bi-weekly basis. So you refine your prediction as it goes forward. You don't want to be doing this every 3 months or 4 months because the gaps between the data is so far apart, you really don't know what changed in the meantime. It's the incremental nature that you can do quickly and efficiently that really helps you. So as I said, at the start of the project, you take a wild guess, and then you kind of refine it down. The complexity one is probably the hardest to do. How do you tell how something changed from one project to the next? But again, if we're talking about layout here, layout is generally preceded by schematic, and schematic is generally preceded by RTL. So you can look at the complexity scaling between the RTL from one project to the next, and use that as a proxy for how is the physical design going to scale. Likewise, when you go from RTL to schematic, you can refine your number. So there are other data types you can use as proxies for some of these scaling factors before you actually get there. And generally, RTL never gets your chip tape out. It's always the back-end physical world. It may start later because RTL wasn't ready, but you can use the RTL as a proxy for how did those things really change before you get the final answer from physical layout. So how does it really work? I mean, that's all great in theory, but what do you do? So it's really simple. The hard part is knowing that the answer is right. Come up with a prediction of how much resource or when tapeout is going to be is fine, but if the answer is incorrect, nobody's going to believe you, and you only really get one shot at that. You screw it up the first time and you lose credibility and nobody will believe you again. So what's more importantly is, how do you know the answer is correct? So starting with something simple, we have a design A in 20 nanometer, and it went through and we know when it started and when it finished and how many man hours it took. And we do the same design in 16 nanometer with limited changes, so the design itself didn't change, this was just porting to a new process node. From that you can get the process scaling factor, 1.5. So the more early blocks that complete, the better your estimate is. You can start doing averaging across blocks. Now you start with design B that had lots of design changes, but it was in the same 20 to 16 transition. It took longer. But you know the process scaling factor was already 1.5, so you already have that from the earlier blocks, which means you can go figure out what the complexity scaling was for that design. And you can do that from RTL, you can do it in schematic, or you can do it from real layout, and you can confirm your numbers as you go through. So you can use other design data as a proxy, and then refine it as you get the block done. Once those early blocks are done, you can calculate both the complexity factor and refine your initial, how do you estimate these things? Maybe your estimate wasn't very good, you go figure out what you did wrong, and you go correct it next time through. And as I said before, you'll have to collect these things into styles because a P&R block and a full custom block is not going to have the same kind of scaling factors and metrics. So you want to kind of group your designs into particular styles and have different scaling factors for each style. So if you have a different design style, you might have a different complexity scaling factor and a different process scaling factor to go deal with. The real thing is for the blocks that start later in the schedule, and those are the ones that are going to start to gate to your tape-out schedule, how do you apply factors for those? And to first order, the process scaling factor, you can just leverage from early designs. So that one's easy. If they have limited design changes, then you know what the resource requirements are going to be. For other designs that have lots of changes, you have to go use schematic or layout or some other metric to estimate what the complexity change was from one design to the next. But you have the process scaling factor, so you can use those two to come out with both the process scaling factor and your estimate on complexity scaling. So to a first order, you can use the early data to go predict the later data. And that's really the key to this is at day one on the project, you're not going to be able to do a very good prediction. It's going to kind of suck. But as you work through the design, you'll get more and more accurate estimates of various scaling factors and various early blocks that you can use to apply for later blocks. So when you get about halfway through the project, your prediction actually starts making sense. What you're looking for is to run this every week or every couple of days, depending on how enthusiastic you are. And you'll see that the predictions are wobbling all over the place, and they kind of settle down to being kind of a stable point. So when you get that stability and you get the repeated stability for a period of time, you know your prediction is probably going to be more reasonable, and you can start then estimating what tape-out date is actually going to be. So what does it all mean? So for our custom layout block that we just talked about, you want to know how many man-hours it took to complete each block in the new process node. You know roughly when they should start and when they end based on the previous projects. The timing of a block starting and ending is very similar. And if you have infinite resources, i.e. not constrained on the resource side, you can now predict what the project timeline is going to be and when you would tape out. Resource is never infinite, but you can make that assumption if you want. But the third answer, which is where did all the resource go, you can now answer that question already. As you track the man-hours over the project and you track the tool license usage, you can go tell finance exactly which design team started when, ended when, what man-hours did they use, what license did they use, and how much did that cost the company. Now, it could be that they need those tools. It could be they were doing something very inefficient and they could change their methodology to use less resources going forward. But you know where the money went. It didn't just pour down the drain into a big black hole. So finance is happy. Next question is how do you factor in the constrained resources? And this really isn't rocket science. If you take the previous estimates of when things start and when they end and how much resource they'll take in the new process node, you can kind of stack them all up and figure out when tape-out is going to be. Of course, if you overlay your resources on your actual max, you find out that you're over-allocating resources, standard project management stuff. You can't use more people than you've actually got in the company. And what you'll do is then start delaying some stuff, because it's always the stuff that starts second that gets delayed, not the early stuff. So you start pushing out the later blocks, which are typically going to be your long haul to tape out anyway. And that gives you a new tape out date that management doesn't really like. And if you look at the resource profile, you find it kind of had this kind of lazy uptick and reaches a peak and then has this lazy downtick until it's tape out. What that means is you're paying a max number of people to work in your company for the entire generation of the project, but you're only using them for about 2 months in that whole period. There's time when they're not idle on the front end or the back end of the project. What you really want to do is change that resource profile. And this is where the analytics start becoming more useful. So we have a profile that looks like that. It's not very ideal. What we really want is something that looks like that, which is use all our resources as much as possible for the longest period of time and have them all finish at the same time. What you really want to do is start either reducing the resource on some early blocks and allocating them to some of the long pole blocks, and for the ones that aren't critical, delay the start of them so that you spread out the resource usage over the duration of the project. What it gives you is a much more efficient profile of curves, Now, this is obviously program management 101. In theory, it's very easy to do. What you really want is the analytics from the previous project and the current project as it's going through to understand where your resource is going and who's using it, who used it before, who's going to use it again, when will it start, so you can preemptively start making these allocations instead of figuring it out halfway through. The earlier you do this and the earlier you can figure out what the right answer is, the less traumatic it is to the design team and the more likely you are to hit that tape-out date. The other thing to bear in mind as well is this is not rocket science, but it's also not a crystal ball. This tells you when you should tape out if nothing exceptional happens. Exceptional stuff does happen. You've also got to pay attention to surprises, new things, features that come in late, stuff that this tool obviously isn't aware of, and factor that stuff in as well. You might have one block that is late because a bunch of new features went in. It won't tell you that until you get started on the block and get partway through. So it's not a crystal ball, it's a tool to help you go figure out what the right thing to do is, and if everything goes well, you'll hit tape out as efficiently as you can, and you deal with surprises as they come up. But it takes you to a point where you can focus on those surprises when they arise, not trying to figure out what everyone else is doing. So, what you really want to do is achieve preemptive resource allocation ahead of time, so you get the most efficient tape out possible. And yes, there'll be some noise in there that you have to go figure out as it goes along, but that's really what you want to do is not be reactive to changes, but be predictive and preempt those changes and corrections as much as possible. And this kind of analytics will let you do that. So, what happens when things go wrong? The early scaling factors for process or complexity can be just wrong. I mean, it's a guess. People make mistakes for honest reasons, and some factors are surprises not really well understood at the start of the project. What I have here is kind of a resource profile of our 20 and 16 nanometer project over time. What you're looking at is for 20 nanometer, you have a certain ramp over time and then a close off to tape out. And assume our early estimate for the resource increase was 1.2, 20% more. So you go off and hire 20% more layout resource in this case to go do your layout. As you go through the project, you realize that, hey, your estimate was wrong. It's more like 60% uptick, not 20% uptick. And it was an estimate, you made a bad call, you want to go correct it. So now you uptick your resource by 60%, but if you were to just increase by 60%, that doesn't solve your problem because you already got halfway through the project and you already burned a bunch of time using less resource than you thought you needed. So you have to overcompensate by hiring additional resource based on what's left to do to keep your tape out on time. You also have the option of delaying tape out, but that's less popular these days. So once you know what the prediction is and you know where you're at and you can start tracking your estimates over time, you get, again, an early indicator that something's wrong, and the earlier you do something about it, the less traumatic it is to the company and the project to go fix it. And you will have that occasion. This is a tool not to tell you what's going to happen, it's to tell you when things are going off the rails or not the way you expect it to be, so you can go do something about it earlier. So, what does all that mean? So it does allow you to do dynamic, active tracking or prediction of problems earlier than most conventional systems. It's predictive, it's not reactive. And it also lets you, well, if I solve it this way or this way or this way, do some interesting what-ifs. How do I go solve this problem? And there's generally more than one answer. You can go figure out what those various answers are and which one is most appealing to you. It also gives you some early indications of any misestimates, and those corrections, if done earlier, are usually less traumatic to your project than if they're done later. So, you can do this all manually. I mean, you can use these tools or you can just do it by yourself. You can write some Python scripts, you can do it in Excel. There's some wizards in Excel, that's a great tool for doing this. This stuff is not rocket science. The problem is it always comes down to the prediction is only as accurate as the data being used. As soon as you start doing this manually or it's not fully automated, you start making simplifying assumptions to make it an easier problem to solve. And those simplifying assumptions quickly erode the accuracy of your predictions. What you really want is some fine-grained data collection that reduces the number of simplifying assumptions that you have to make. And you want to be able to rerun it frequently so that you don't get caught by one-off noise or things. You want to be able to average this stuff over time and kind of get out some of the one-off noise that will come up. You will need to accommodate exceptions. You don't want a fixed model. You need to be able to have this programmable. You want to be able to access it with a language where you can start adjusting the data and making project-specific and company-specific assumptions in there. It's not going to be working just from a generic perspective from an EDA vendor. This is your project. It's very different from everyone else's project. You need to be able to tune that for your needs. And then last thing is you need to validate this. If you're expecting to go buy this stuff and have it predict your next project, then you're living in a fantasy land. What you really need to do is run this in parallel with an existing project and use the prediction to find out how accurate the model is and tune it. Only when you validate it against an existing project can you start looking at the next project and having some confidence that it will be there. We were running this at 28 nanometer and 20 nanometer and 16. We only got reasonable predictions at the 20 node and at the 16 node because we already had a lot of validation in place. So an inaccurate prediction is worse than no prediction. If you come up and say, hey, Tapeout's going to be delayed by 3 months, and it isn't, that wouldn't be very popular. Even worse, if you say Tapeout's going to be on this date and it turns out to be 2 months later, it'll be even less popular. It's got to be right. Too much one way or the other is not a good thing. So, also what we want is a metrics database that can suck in a bunch of data and allow us to do Python-based queries. We like Python. It's a very flexible language. It lets us do a lot without thinking about coding. You can build the system yourself. I mean, you can go install a machine, install Python, make Mongo work, do it all yourself. Of course you can, but why would you do that? Doing big data well is not easy. You can do it badly, but what you really want is to be LPAs that can query that data very quickly and efficiently. And I don't want to become Google. I'm not in that business. It doesn't help my customers to be able to understand how big data works. I want to be able to understand what the big data means, not how to do it. So why would you buy it from a database vendor? They know how to do this. They've been doing it for a couple of years. They know what matters. They know how to make it efficient. They know how to solve the problem. They know how to solve your problem, but they know how to solve the database problem, how to get a lot of data in there and have it queryable efficiently. So at least from a Xilinx perspective, we made the decision to work with ICManage to build the system we want rather than build it ourselves. With hindsight, I'm very happy with that choice. It means that we get to focus on our problem, not on how to make the system work. But if you want to do it yourself, it's not rocket science. You can do that. But I just want to point out this is a real tool that you can use. It's not slideware. From a collection perspective, there's a lot of data in there. You can suck out your metrics, but those metrics are just meaningless numbers unless you do something useful with them. So you know your project's different from my project. I know how to predict my project. I have no idea how to do yours. The point is the system gives you a way to produce these graphs with a Python-based language underneath that lets you tune the data and filter it and scale it and factor it the way you want to see it. So it's not a data-to-graph solution. It's a data-to-programmable API to graphing solution that you can tune what graphs are presented and how the data is presented so that your PMs and program managers and design leads can go look at the data and have it make sense to them as opposed to try to having to interpret it after the fact. So the conclusions, what we were looking for was a system that could collect a very large amount of raw data from both our data management system, which has a lot of the check-in, check-out and fine-grained data management data. We also wanted to look at external sources for various analysis tools and flows, because those also matter when licenses get checked in, checked out, how many DRCs we've got, if anybody's even running DRC. Usually the biggest indicator you have a problem is the fact that there is no data. They should be running DRC by now and they're not running it. Why aren't they running it? So there's also a lot of external sources that we want to put in the same system. And then we want to find custom prediction models. The models are custom to Xilinx. They work for us. They wouldn't work for anybody else, probably not even Altera. Every model, every company has their own models and the way they work. They have their own long poles. It's got to be tunable to what you guys do, not just a generic canned solution from an EDA vendor. We want to know when we're going to tape out. Obviously, that's a big deal. And it's not just when should we tape out. You will obviously have problems if your tape-out data is predicted to be too early. Nobody believes it, so they don't work hard towards it, and tape-outs tend to slip. Knowing when you're going to tape out lets you line up the back-end resources for silicon verification and packaging and QA and all the rest of the processes depend on that data a great deal. You want it to be as accurate as you can be. And for us, engaging with a database vendor to make that system work was good business sense for us. I don't want to become Google. I just want to use the system to solve my problem. I don't want to be in the big data business. So the real question is, how accurate is it? At least for Xilinx, I can tell you that we tracked the man hours using the system, and because they were directly costed in finance, there was a separate effort on the finance side to go track the man hours independent of ICManage, using spreadsheets and email and their existing system. ICManage, the system that we have was within 2% of actual over the course of an entire project in terms of man hours. And we were 2% under, and partly that is because some design teams are still using private libraries for doing layout resource. They counted for that 2-3%. Obviously, if it's not ICManage, we can't track it as active work because they're not using it. We can see licenses getting checked out and checked in, but not corresponding to any ICManage check-ins, so we know something's going on. But that's why we're 2% under. In terms of when we're taping out, Our estimates are typically published around 6 months before tape-out on a typical 18-month, 2-year project. That's about half to 3/4 of the way through. And at that point, 6 months before tape-out, our predictions are within about plus minus 1 week. Those are typically not the top-down project management schedules that are in place at that time. But as you go through that past 6 months, we've been within a 2-week window of when we actually tape out. Now, again, your mileage will vary. It all comes down to how you do it and what assumptions you make and what corners you cut and how good you are at tracking your estimates and refining them as you go forward. You can do a bad job and come up with a really bad estimate. One thing we did find was even the simplest assumptions make a big difference to the prediction and the accuracy of it. The devil's in the details. You really need details. The first part of what you do is a predictive model on what's normal, what you should expect to see for all your design blocks. Once you get partway through the project and you get some confidence in that model, then you can start looking for places where your design team is starting to depart from the prediction. Now, it could be that they're right and the prediction's wrong, or vice versa, you don't know. But the important point is you're looking for those departures so you can go debug and figure them out. Once you've figured out that the team is departing and it's a real departure, then you can start looking at what changed. Was there more complexity? Is it harder to do? Is there something fundamental about the design that is different? It lets you start tuning the predictive model to accommodate that change. And more importantly, what you really want to do is when you see those departures is try to figure out how to apply more resource to that block to get it back on schedule. To a first order, why they're late doesn't really matter. The fact that it is the important point. And what you typically do, what we have started doing is cannibalize resource from projects that are on schedule or blocks that are on schedule to apply to the ones that are behind so that you'll finish at the same time. And I'm saying counterintuitive, but you're already in a situation where you're blowing schedule. You want to minimize the impact of that. So yes, you use it in 2 ways. One is predictive in terms of what's normal, and then you start looking for aberrations from normal and figuring out what to do about them.
A question on the scaling factors that you used. Is there a way to learn those scaling factors? For example, based on design size, complexity of constraints vis-a-vis technology, and things like that. So otherwise, how do you get these 1.2x versus 1.4x versus these numbers?
Yeah, what we've experienced is, we can put our designs into certain buckets. There's mixed signal designs, there's PNR designs, and there's kind of more full custom designs. The process scaling factors for those tend to be somewhat different, but very consistent within that subtype. So it's kind of figuring out what you have in your chip and how to bucket them is kind of the first step. The complexity scaling is really, every design can scale differently for that. Really what you're looking for is pre-triggers or pre-predictors. If you're worried about layout resource, you're looking at schematic or RTL for the same design to figure out how much it changed from one to the next, one project to the next. You can use those as early estimates for what the complexity scaling would be, and then you refine as you go forward. So yes, you start off with an estimate, which is really why you don't want to predict tape out at the beginning of the project. It's a nonsense number. What you want to do is as you go through the project, you'll see that the variation in those predictions starts to settle down. If you do them every week, they'll be swinging all over the place, and then they'll kind of settle down to a common point. That's when you kind of know you got the buckets right and you got the predictions right, and once that variation starts coming down and your error bar starts to close down, then you can start using it as a predictive model, and then start looking for departures from the predicted model and what that means for tape-out. So it's work. It's not just, you don't just push the button and it happens.
How much data do you need to do what you talked about? And are the models flexible, or do you have to tune it after you go through a couple of cycles or something to adjust those models for new predictability or new things that you're doing?
So we track every single file checkout and single check-in by whom, when, and every single license checkout and license check-in. So it's a fairly significant amount of data. We do maybe 5,000 check-ins a week, and each of those check-ins can be either one cell or hundreds of cells. So the volume of data is quite significant from that perspective. In terms of tuning and iterating, yes, what we did was went through one project where we just kind of collected and didn't even try to predict because it was pointless. Once you have that side data, the second project is where you go through and you start predicting, but you keep it private so you can correlate whether your methodology works or not, and you tune it. The second project tells you that you can predict the right answer based on what actually happens. And your third project is where it actually starts to become useful and you can start using that data going forward. So yes, there is a learning tuning cycle. The key for us was we wanted to be able to intercept the raw data to presented data with a programming language that we could tune and adjust, and with the Envision system, that's Python. So we can collect all the raw data, collapse it, create metrics, and then back them, scale them, weigh them, however we want to come up with that final answer.
So how long did it take you to finally get to your final tuned model, so to speak?
The first project was a 28, and we just collected data on that pretty much. The second set of projects were in the 20 nanometer node, and also we tape out multiple projects. The first one, our prediction was within probably about plus or minus 2 to 3 weeks in terms of tape out, and the man-hours resource has always been within that about 2% window of tracking. The third project, our internal team stopped tracking man-hours because the answer they were getting from our system was on the money, so they just stopped doing it because it was a lot of effort and no value add. But the tape-out prediction closed down to about a plus minus a 2-week window, so plus minus 1 week.
Have you applied this to any other than just, looking at tape out, time to market? Have you applied it to bug tracking, issue tracking, verification, any other part of the...
Our initial focus are really 2 important metrics. When are we taping out? Can we have a more predictive model for that instead of reactive? And man-hours. We obviously hire a lot of contractors in addition to full-time, and we pay them, and that has a big budget impact. So we want to know how many we're hiring, for how long and where, and who uses them. So those are the initial 2 metrics that we were interested in getting very good, accurate predictions for. We will deploy this into other areas of our design process, but our initial focus was on those 2 areas. Started this process off trying to predict tape out and where a resource was going from a project level, but you have to do that at the design level so that the project roll-up kind of makes sense. What we did find was a lot of our design teams want to know how much resource they're using, whether they're on track and where things are going. So we were getting a lot of requests from them to, well, I don't care about the rest of the chip, just tell me about my stuff. And we went down the path of, well, we can do a presentation layer. Silicon companies tend to not do those things well. It's not something we're either good at or have a lot of interest in doing, to be honest. So you end up giving them raw data in spreadsheets and they figure it out. So what we did find from the design teams was they were very interested in being proactive about their own resource and their own tracking and looking for aberrations early for the same reasons that we were doing this. The sooner they know about a problem, the sooner they can delete it. But they want to be able to do specific drill downs of, I just want to know about this IP or this set of IPs or this variant because I own it, or very subsets of the data, not the complete set. The charts that I presented allow you to go do that kind of drill down. I really care about the project level stuff and how it rolls up, but they want to know just for these 2 IPs, how do I compare last project to this project, or these 2 IPs that are supposed to be the same, how do they compare, or I own this one, what's this one doing? So a lot of it lets you do that kind of low-level drill down into specific data types and specific IPs, and then look at the subset data just for that stuff. So a lot of design teams are using it from that perspective. They want to know their part of the world, not the whole context. And that was kind of interesting that what came out of a big picture actually turned out to be something useful for the design teams from a very low-level specific perspective. And I skipped through them because, well, interest of time, and they make sense to me because it's my project. And the data in there is generic, so when you read it, if you're Altera, don't try to assume that's what we're doing. It's just made up data. But yes, it gives you a feel for the type of reports that you can do very efficiently and quickly. And that's really what's important. And a lot of them are customizable. Again, you can tune the data via Python so that your end user doesn't have to even be a programmer, they just see the reports they want.